Well, hello, thank you very much. I'm going to talk today about a rather unusual project that we are engaged with, ANU, using AuScope seismic instruments. And it's about locating unexploded ordnance with AuScope instruments in a rather unusual setting. My co-authors are Michelle, Megan, Brian, and particular thanks to Daniel Stevens of the Australian Defence Force, whose original idea this was. Okay. So we all think of forensic seismology typically in terms of detecting things like nuclear weapon testing, and Australia's very active in this area, being a main contributor to the international monitoring system, both in seismic and infrasound. Here we've got a picture of the Warramunga seismic array in the Northern Territory. But there are other types of forensic seismology, and here's one that I found particularly interesting and caught a lot of attention back in 2007 with Garrett Uhler of the Washington University of St. Louis, whose now famous AGU abstract showed an array here in Africa, where the seismic array is across the entire country, as in on the left here, and on the right they found a signal that occurred with no move out. That it seemed to be happening everywhere at once, and was later found to be the goals being scored by the Cameroon national side, and people celebrating in their traditional manner by jumping up and down and creating a nice vertical seismic source. And thus was born the legend of the footquake. And such things have been recorded many times since. This was a puzzle when it first appeared, and really it's anthropogenic seismic signals. Here's some more anthropogenic seismic signals. On the left-hand side, intrepid band of AuScope researchers recorded the Viking clap from the rugby league game between the Raiders and the Panthers in 2009. Here we can actually go through, and thanks to Michelle for this figure, and find the tries of different people running across the line and the excitement of the crowd. Unfortunately, the Raiders lost. On the right-hand side, thanks to Caroline Ekin and co, is a similar seismic record of the RAF flyover of Canberra on the 100th anniversary of the RAF, with spectacular flyovers of many aircraft, all creating various types of seismic recording. Here, so you can see the roulettes in the bottom right corner. That was recorded on the Parliament House basement website, seismometer. So the particular problem we have here is when we were visited once by Daniel, the problem was the one of detecting unexploded bombs during testing from aircraft. Now, when bombs fail, they go missing every year on weapon sites, and it's an expensive and dangerous exercise to locate and dispose of them. Defence do this with painstaking work and care, and it's a highly skilled and dangerous job, and sometimes it can take weeks or months, and bombs can depart from the impact and outside of the range. You just don't know when one's not going to explode. So the question was, how can you detect these, or whether you can detect these with seismic instrumentation? And that was the proposal. We worked with Daniel to try a feasibility test out using AuScope instrumentation. We put essentially 2 arrays around test sites that were about to be used. On the right-hand side here, you can see what we call the inert array. We had a high explosive array and inert array. So the Air Force conveniently dropped concrete inert bombs. We knew they weren't going to go off, so we could actually record some inerts, as well as some high explosive bombs as part of their normal testing. And we recorded all of them and analyzed them. Now, here I'm going to quote directly from Brian's analysis of it. On the left-hand side, you see a 500-pound inert bomb, and on the right-hand side, a high explosive. P waves on the left-hand side are about 4,500 meters a second. The velocity of S is about 2350. You can see rally waves and S waves. You can certainly see the inert bomb. And on the right-hand side, much higher amplitude, 3-component data, where we can see also an acoustic wave coming in later, and that's because of the blast on the explosion. So you can actually reasonably straightforward to tell the difference between an inert and an explosion. And on the right-hand side, we actually see the same trace as the left, the inert, where essentially that's a double bounce. It looks like we've got a bouncing inert bomb there. So some frequency time analysis, looking in more detail, can show essentially we can pick the arrival times of P and S either directly on unfiltered or on high pass filter data using standard STA LTAs. So we can actually get good measurements of the onset times of P and S waves. Particularly here, we use that data to try and use earthquake location type mechanisms. Now here, we know the thing is on the surface, and it turns out that you can actually locate these things with sort of standard iterative least squares solutions. We tailored this to the particular problem, and it's relatively insensitive to assumptions about the Earth speed model. So we can get not only a good location, but most importantly, an error ellipse around. And it turns out that in the field, this worked out reasonably well with tens of meters of accuracy rather than hundreds of thousands. The ring is about 2 kilometers away. So we've got high accuracy from multiple methods overlooking each other. And it turns out that this is now being used. I will play the video.
Start in 5, 4, 3, 2, 1.
So the way the technology works is we use a distributed array of sensors that measure seismic and audio energy which is released from a bomb when it hits the ground. But that bomb can hit the ground and bounce. It can hit the ground and bury itself underneath and continue to travel. That bomb could be almost anywhere.
Detecting the exact location of a bomb that's hit the ground and hasn't functioned can prove quite difficult. If we can get a starting location that's quite accurate, make our job a lot quicker and more efficient. Because it can take days or weeks or months to find a bomb sometimes.
Last year we were working on another prototype which was focusing on audio only. Now with our collaboration with the Australian National University, we are now changing tack and we are focusing on the seismic side of the house. Seismology is a dark art. It's not something I wanted to do alone, and so I'm very thankful to have the Australian National University there with us.
This project's challenged us because most of the work that we normally do within the Research School of Earth Sciences is looking at distant earthquakes, so what we call passive seismology. And in this case, we're looking at explosions, and they have quite different signals.
So with regards to the accuracy of the system, in our preliminary phase, we've found that it can determine the location of an exploded bomb within about plus or minus 10 metres, and an unexploded bomb within about plus or minus 25 metres.
This innovation, like a lot of other things that come through to Plan Jericho, could provide better capabilities for Air Force and thus moving us to our 5th generation concept.
In the innovation process, you have to be willing to change, and you have to be willing to change fast and learn from your failures.
Roger that, flight control. See you on the other side.
I love the challenges. Every day it is different. It is so dynamic. You don't know what is coming the next day. You can set out a project timeline all you want, but that is going to change every single day, and that's what I love about it.
So to sum up then, what have we learned? Well, key outcomes are that we can detect ordnance impact, certainly high explosions, and discriminate them from inerts. Inerts can be seen, we can see seismic phases on them. Picking is possible using very simple automated methods to get an onset time, particularly a P time. We can use earthquake location algorithms, slightly adapted for the purpose, to get reasonably accurate locations and uncertainty, which is key. And we've used off-the-shelf components in terms of geophones. I'll finish with a quote from Daniel himself, who says that the best results are born from aligned minds across misaligned professions. And I couldn't put it better myself. It's been a wild ride, and there's lots of good prospects for the future for this sort of technology to take off. So I'll leave it there. Thanks.